Hello students, in today's class we will study about periodic trends in properties of elements. There are many observable patterns in the physical and chemical properties of elements as we descend in a group or move across a period in the periodic table. For example, within a period, chemical reactivity tends to be high in group 1 metals, lower in elements towards the middle of the table, and increases to a maximum in the group 17 nonmetals. Likewise, within a group of representative metals, say alkali metals, reactivity increases on moving down the group, whereas within a group of nonmetals, say halogens, reactivity decreases down the group. But why do the properties of elements follow these trends, and how can we explain periodicity? To answer these questions, we must look into the theories of atomic structure and properties of the atom. In this section, we will discuss about the periodic trends in certain physical and chemical properties and try to explain them in terms of number of electrons and energy levels. So please note down all the important points in this lecture, as I will not be describing or displaying on the screen in the text format, but I will explain all the concepts. I welcome you once again. Trends in physical properties. Please see the periodic table displayed on your left hand side of screen. Here the periodic table is described in brief. Let us quickly recap what we have studied in our previous video lectures. The term periodicity is used to indicate that some characteristic properties occur in the periodic table after definite intervals, however, with a varying magnitude. Thus, after starting from a certain point on the periodic table, we are almost certain that the movement in a particular direction will show steady increase or decrease of a said property. Modern periodic table arranges the elements in the order of their atomic numbers in 7 horizontal rows called periods. These are periods, 7 horizontal rows which are called periods, and 18 verticals columns. These are columns. There are 1 2 3 up to 18 columns, vertical columns called groups or families. The atomic numbers in a periodic table in a period are consecutive. So in the period, the atomic numbers are consecutive, whereas in the group they increase in a pattern. So in a group they increase in a pattern. Elements of the same group will have similar valence shell electronic configuration and therefore exhibit similar chemical properties. So I will repeat this. Elements of the same group have similar valence shell, that is electronic configuration, and therefore exhibit similar chemical properties. However, the elements of the same period have incrementally increasing number of electrons from left to right and therefore have different valencies. So please note here the elements of the same period, say for example this period, will have increasing number of electrons from left to right and therefore have different valencies. Four types of elements can be recognized in a periodic table on the basis of their electronic configuration. These blocks are S block, this is a S block, P block is here, D block, F block and E block, D block, F and F block. Elements with one electron in one s orbital occupies a unique position in the periodic table. So this hydrogen occupies a unique position in periodic table. Metals comprise more than 78% of the known elements. Non-metals, which are located at the top of periodic table, are less than 20 in number. So non-metals are less than 20, whereas more than 78% of the known metals and known elements are metals. Elements which lie at the border of line between non-metals. Metals and non-metals are silicon, germanium and arsenic. They are called metalloids or semi-metals or sometimes semiconductors. Metallic character increases with increasing atomic number in a group, whereas decreases from left to right in the period. The physical and chemical properties of elements vary periodically with their atomic numbers. So with this recap, we will proceed to discuss the trends in physical properties. There are numerous physical properties of elements such as melting point, boiling point, heat of fusion, vaporization, energy of atomization, etc., which show periodic variation. However, in this section, we will discuss the periodic trends with respect to atomic and ionic radii, ionization enthalpy, electron gain enthalpy, and electron negativity. These 5 subsections we will be covering in this video lecture. Atomic radius is of 3 types. Metallic radius, it is taken as half the internuclear distance separating the metal cores in the metallic crystal. For example, the distance between two adjacent copper atoms in solid copper is 256 picometers. So, the distance between two adjacent copper atoms in a solid copper is 256 picometers. Hence, the metallic radius of copper is assigned a value 128 picometers. Another type of radius is covalent radius. The distance between two atoms when they are bound together by a single bond in a covalent molecule, and from this value the covalent radius of element can be calculated. For example, the bond distance in the chlorine molecule Cl2 is 198 picometers. The bond distance is 198 and half the distance is 99 picometers. So here you see it is atomic radius is 99 and is taken as the atomic radius of the chlorine. Van der Waals radii is one half of the distance between nuclei of the two non-bonded adjacent atoms belonging to two neighboring molecules of elements in solid state. We will study about van der Waals equation in subsequent lectures. So please note from the table, contents of the table. The atomic radii decrease while going from left to right in a period and increase with atomic number in a group. So here you see for period 2, here the first line lithium beryllium, boron, carbon, nitrogen, oxygen, and fluorine. The atomic radius is varying from 150 to decreasing. It is decreasing from 152 in the case of lithium to 64, and it is systematically decreasing as we move from left to right, and this atomic radii increases as we go down from in the group. In the group, see, this is a group. Here if you take a group, the atomic radius increases. For example, group 1 group 1, it is 152, 186, 231, 244 and 262. This is for group 1, whereas in group 17 also it is increases as we go down. See, it is for fluorine it is 64, for indium 134, for another element it is 140. So it is increasing. This trend is also shown in the graphically on your screen. Please see the graph. The first graph, this graph shows variation of atomic radius with atomic number across the second period. This is pertaining to second period, this graph. Whereas it is the next graph, that is on the extreme right side, it is variation of atomic radius with atomic number for alkali metals and halogens. Please expand it and refer in the diagrams. If you are not able to see properly, please open your textbook and interpret the graphs as per your convenience. So this arrow shows the atomic radius decreases. See here, for lithium it is large and it is decreases from left to right. Ionic radius. The removal of an electron from an atom results in the formation of a cations, whereas gain of an electron leads to an ion. This can be expressed. So cation formation is the loss of an electron, and anion formation is the gain of electron. Both are reflected on the screen. The ionic radii can be estimated by measuring the distance between cations and anions in ionic crystals. In general, the ionic radii exhibit the same trend as atomic radii. A cation is smaller than its parent atom because it has fewer electrons while its nuclear charge remains the same. The size of an ion will be larger than that of the parent atom because the addition of one or more electrons would result in the increased repulsion among the electrons, that is repulsion between electrons, and it decreases the effective nuclear charge. For example, the ionic radius of fluoride ion Fe minus is 136 picometers, whereas the atomic radius of fluorine is only 64 picometers. Similarly, the atomic radius of sodium is 186 picometers compared to the ionic radius of 95 picometers for Na+. Now we will define isoelectronic species. When we find some atoms and ions which contain same number of electrons, we call them isoelectronic species. These are isoelectronic species are the atoms and ions which contain the same number of electrons. For example, O2 minus, F minus, Na plus and Mg2 plus have the same number of electrons, that is 10. But their radii would be different because of their nuclear charges. The cations with greater positive charge will have a smaller radius because of the greater attraction of electrons to the nucleus. An ion with greater negative charge will have larger radius. In this case, the net repulsion of electrons will outweigh the nuclear charge and ions will expand in size. Let us answer one question. Which of the following species will have the largest and the smallest size? Mg, Mg2 plus, Al and Al3 plus. Answer. We know that the atomic radii decreases across a period. Cations are smaller than their parent atoms. So among isoelectronic species, the one with the larger positive nuclear charge will have the smaller radius. Hence, the largest species here is Mg and the smallest one is Al3 plus. Ionization enthalpy. It is the energy required to remove the most loosely bound electron from an isolated atom in gaseous state for 1 mole of an element, and it is expressed in kilojoules per mole and can be written as M in gaseous state plus ionization enthalpy gives M plus in gaseous state plus an electron. If gaseous atom is to lose electrons, they can be removed in succession and not simultaneously. This is known as successive ionization energy or potential. That means it can be also written as IE3 is greater than IE2 greater than IE1. Here IE3, IE2 and IE3 are the ionization enthalpy first order, second and third order. The screening effect or shielding effect. In a multi-electron atom, valence shell electrons experience less attractive force due to repulsion between inner shell electrons and valence electrons. This is called screening effect or shielding effect. Now we will quickly go through the factors affecting ionization enthalpy. These factors are the size of an atom. So, ionization enthalpy is inversely proportional to the size of atom. That is 1 over size of atom. Nuclear charge. Ionization enthalpy is directly proportional to the nuclear charge. Screening effect. The screening effect, ionization energy is directly proportional to 1 over screening effect. The type of orbitals involved, that is S, P, D or F, it is explained in the next slide. So completely or half-filled orbitals, it is comparatively difficult to remove the electrons from these orbitals being more stable. So it is comparatively difficult to remove electrons from completely or half-filled orbitals. electrons from orbitals. Please observe the first ionization enthalpy is expressed in kg per mole given in table number 3 on your screen. Let us quickly go through some important observations. The metal group 1, that is group 1 is here, lithium, sodium, potassium, etc., have the lowest ionization enthalpies in their respective period. So these are lowest in their periods with respect to their period. Say for group 1, for period 1, hydrogen has 1311 and lithium has 520, which is lowest, and so on. Point number 2 is the noble gases, that is listed in group 18, helium, neon, argon, etc., have the highest ionization. So lowest is in 1 and highest is in group number 18. It is because the energies required to remove electron from a stable fully filled shell is very large. That is, to remove electrons from this any of the elements in this group is very large. Point number 3 is the values of ionization energies do not increase smoothly. That is, the first ionization enthalpy of boron is lower than the beryllium. See here, boron, the ionization enthalpy of boron is 801, whereas for beryllium it is 899. So, boron has lower ionization enthalpy than beryllium. Similarly, the ionization enthalpy of aluminum is lower than that of magnesium. The first ionization enthalpy of oxygen is lower than that of nitrogen. The first ionization enthalpies of beryllium and magnesium are higher than those of their preceding elements because electrons are removed from the fully filled orbitals. In small atoms, the electrons are tightly held, whereas in large atoms, the electrons are less strongly held. Thus, the ionization enthalpy decreases as the size of the atom increases. You can see the variation here shown in the graph. The first ionization enthalpy of nitrogen is higher than that of oxygen because from nitrogen the electron is to be removed from half-filled p orbitals. When an electron is removed from an atom, the effective nuclear charge, that is, the ratio of the number of charges on the nucleus to the number of electrons increases. The ratio of number of charges to number of electrons increases. As a result, the remaining electrons come closer to the nucleus and are held more tightly. The removal of second electron before therefore removal of second electron requires more energy. I will read once again. The removal of the second electron after the removal of the first becomes more difficult and requires more energy. Mg plus is a smaller than Mg atom. The remaining electrons in Mg plus are tightly held. The second ionization enthalpy is therefore more than the first ionization enthalpy. Since orbitals s, p and d and f have different shapes, the ionization enthalpy depends on the type of electrons removed. Example, an electron in s orbital is more tightly held as compared to an electron in the p orbital. It is because s orbital is nearer to the nucleus as compared to p electron. Hence, s electron is tightly bound to the nucleus. Similarly, a p electron is more tightly held than d. Compared to d, p is more tightly held, and d is more tightly held as compared to the f electron. If all other factors are equal, the enthalpies, ionization enthalpies, are in the order of S greater than P, greater than D, and greater than F. So we will answer one question. The first ionization enthalpy, delta IH, values the third period elements like sodium, magnesium, and silicon are respectively. The values are 496, 737, and 786 kilojoules per mole. Predict whether the first delta IH, that is ionization enthalpy value for aluminum, will be more closer to 575 or 760 kilojoules per mole. Justify your answer. Please read the question once again. The first ionization enthalpy delta IH value of the third period elements are sodium, magnesium, silicon are given as 496, 737 and 786 kilojoules per mole. Predict whether the first delta IH value for aluminum will be more closer to 575. So justify your answer. Answer is it will be more closer to 575 kilojoules per mole. The value of aluminum should be lower than that of magnesium because of the effective shielding of 3p electrons from the nucleus by 3s electrons. Electron gain enthalpy. Electron gain enthalpy is the energy released from 1 mole of neutral atoms in a gaseous state when electron is accepted by each atom. For example, if X is an atom, a gaseous atom, when it gains an electron, then the energy is released for 1 mole of neutral atoms in the gaseous state when electron is accepted by the atom X. Another example is chlorine in gaseous state. When it accepts an electron, it becomes chlorine minus in gaseous state. And the energy released is delta E of Eg. That is, the electron gain enthalpy is, the value is minus 349 kilojoules per mole. This is shown in the group 17 chlorine against in the table. Every atom in general has a tendency to gain or lose electrons in order to acquire a noble gas configuration. So it is a general tendency for electrons to gain or lose electrons in order to acquire a noble gas configuration. The atom which have 5, 6 or 7 electrons in their outermost shell show tendency to accept electron and attain the nearest noble gas configuration. Halogens, for example, have 7 electrons in their outermost orbit. Thus, they show a tendency to accept one more electron and attain the nearest noble gas configuration. The energy change delta Eg, represented by the symbol delta Eg, E of Eg, for this process is called electron gain enthalpy. The negative value here in the table shows the release of energy. and hence tendency to greater stabilization. When energy is released, there is a tendency to greater stabilization. The electron gain enthalpy becomes more in negative from left to right. From here to here, it is more in a period. In a period, electron gain enthalpy becomes less negative as we go down the group. As we go down the group, it becomes less negative, showing that the electropositive characters of the atoms released. We will answer one question. Which of the following will have the most negative electron gain enthalpy and which the least negative? And which is the least negative amongst phosphorus, sulfur, chlorine and fluorine? Explain your answer. Electron gain enthalpy generally becomes more negative across a period as we move from left to right, as we have seen from the table shown on your screen. Within a group, the electron gain enthalpy becomes less negative down a group. So, the negativity also decreases, less negative. However, adding an electron to p orbital leads to greater repulsion than adding an electron to the larger 3p orbital. Hence, element with most negative electron gain enthalpy is chlorine, as shown in the table, and the one with least negative electron gain enthalpy is phosphorus. Electronegativity. A qualitative measure of the ability of an atom in a chemical compound to attract shared electrons to itself is called electronegativity. That is, electronegativity is a measure of the ability of an atom in a chemical compound to attract shared electrons to itself is called electronegativity. It is an indicator of the extent of attraction by which electrons of the bound pair are attracted by an atom linked by this bond. Unlike ionization enthalpy, the electron and electron gain enthalpy is not measurable. That means electron gain enthalpy is not a measurable quantity. However, a number of numerical scales of the electronegativity of elements, namely Pauling scale, Mulliken-Jaffe scale, Allred-Roschow scale, have been developed. Table on the screen shows the electronegativity of elements on Pauling scale. The electronegativity of a given element is not constant. It varies depending on the elements to which it is bound. Though it is not a measurable quantity, it does provide a means of predicting the nature of force that holds a pair of atoms together. That is a relation that you can explore it later. Electronegativity generally increases across a period from left to right. You can see electronegativity increases in a period from left to right and decreases down the group, say from fluorine to astatine. In the periodic, the attraction between the outer or the valence electrons and the nucleus increases as the atomic radius decreases in a period. the electronegativity also increases. We can just conclude these descriptions by referring to the periodic table. So, here you see atomic radius decreases from left to right or increases from right to left, and electron atomic radius decreases or increases from top to bottom, that is across a group. Then electron ionization enthalpy increases from left to right, and similarly ionization enthalpy decreases from top to bottom or increases from bottom to top. Ionization enthalpy. Now electron gain enthalpy. Electron gain enthalpy increases from left to right and increases from bottom to top. Then electron negativity increases from bottom to top and left to right. This is the summation, is the summary of what we have studied about these items. Multiple choice questions. Question number 1. Few values are given in the table in the direction from left to right and top to bottom. This is left to right and top to bottom. Predict the property which could be depicted in the table. Please analyze the data given in this table and answer the question. 4 options are there. Option A, atomic number. Option B, ionization enthalpy. Option C, atomic radius. And option D, electronic gain enthalpy. So which is the correct answer? You please pause the video and mark your answer. Meanwhile, I will give the correct answer. So it is, the data is atomic radius. Atomic radius increases from top to bottom, and atomic radius decreases from left to right. So you mark option C. Next is, which of the following statements regarding variation of atomic radii in the periodic table is not correct? 4 options are given, so you have to mark which is not correct. Please read the question, pause the video and give the answer correctly. And I will also give the explanation. The size of atom decreases with increase in atomic number in a period. But here it is given with increase in atomic number it has given. So option D is wrong answer. So you mark it. Ionization radius in a group while moving down remains same from top to bottom, decreases from top to bottom, increases from top to bottom. First increases and then it decreases. Please pause the video and mark the correct answer. The ionic radius in a group increases from top to bottom since one energy shell is added with each period. So option C is the correct answer. Please mark it. Next question. K plus and Cl minus ions are isoelectronic. Which of the statement is not correct? So 4 options are given. Both K plus and Cl minus ions contain 18 electrons. It is correct. Both K plus and Cl minus ions have the same configuration. This is also correct. K plus ion is bigger than Cl minus ion. This is wrong. And D, Cl minus ion is bigger than K plus ion. So this is correct. Please mark the answer. the wrong statement. K plus ion is bigger. So actually K plus ion is smaller than Cl minus. Next we will take next question. Which of the following group represents a collection of isoelectronic species? Atomic number of cesium 55 and bromine 35. So we have to identify the isoelectronic species in the group. Option A, Na plus, Ca2 plus and Mg2 plus. Option B, N3 minus, F minus Na plus. Option C, Be, Al3 plus Cl minus. Option D, Ca2 plus Cs2 plus and Br. Please pause the video, analyze and mark the correct answer. Meanwhile, I will give the correct answer. All the three species of the option B are N3 minus F minus Na plus have the same number of electrons 10, hence are called isoelectronic species. So mark the correct answer as B. Which of the following transitions involve maximum amount of energy? So four options are given. M splitting and losing one electron, M minus losing two electrons and formation of M plus, M2 plus forming M3 plus and accepting one electron, and M plus giving M2 plus plus one electron. So we have to mark the maximum amount of energy. So here in this IE3, in this option C, IE3 is greater than IE2 greater than IE1. Hence option C is the correct answer. Next question. Which group of elements show lowest ionization enthalpy? Option A, alkali metals. Option B, alkaline earth metals. Option C, halogens. And option D, noble gases. Alkali metals show lowest ionization energy because of higher radii, due to which the outermost electron is far from nucleus and can easily be removed. Hence, the correct answer is A. Please mark it. Option A is the correct answer. Which of the following elements will have highest second ionization enthalpy? Please read the question once again. Option A, 1s square, 2s square, 2p6, 3s square. Option B, 1s square, 2s square, 2p6, 3s1. Option C, 1s square, 2s square, 2p6, 3s square and 3p square. Option D, 1s square, 2s square, 2p6, 3s square and 3p3. So please read the question, pause the video, read the question once again. I will give the correct answer. After losing one electron, the atom will get a stable configuration and its second ionization energy will be high. Hence option B is the correct answer. Please mark it. Next question. Of the metals beryllium, magnesium, calcium and selenium of group 2 in periodic table, which has the least ionization enthalpy? Option A, Be, option B, Ca, option C, Mg, option D, Sr. So you have to identify the element metal which has least ionization enthalpy. Please pause the video, think for a while and mark the correct answer. Down a group, ionization enthalpy decreases. Hence, option A is the correct answer. Next question. Why do noble gases have positive electron gain enthalpy? So options are given, answers are given. A. It is difficult to add an electron due to small size. Option B. It is difficult to add an electron due to high electronegativity. Option C. It is difficult to add an electron due to stable configuration. Option D. It is difficult to add an electron due to high electron affinity. Four options are given. You please pause the video, analyze. I will give the correct answer. Due to stable configuration, they do not accept an electron and hence they have positive electron gain enthalpy. Means option C is correct. Please mark it. Option C. Next question. As we move from left to right, the electronegativity increases. An atom which is highly electronegative has four options are there. So option is large size atom which has highly electronegative large size. B. Low electron affinity. Option C. High ionization enthalpy. And option D. Low chemical reactivity. Please pause the video and examine. I will give the correct answer. The correct answer is it is difficult to remove an electron from a highly electronegative element. So the correct answer is C. Please mark it. So an atom which is highly electronegative has high ionization enthalpy. Next question. Which of the following arrangements represent the correct order of electron gain enthalpy? Option A. Oxygen less than sulfur less than fluorine less than chlorine. Option B. Chlorine less than fluorine less than sulfur less than oxygen. Option C. S less than O less than Cl less than F. D. F less than Cl less than O and less than S. Please pause the video and mark your answer. Electron gain enthalpy becomes more negative across a period while it becomes less negative in a group. However, electron gain enthalpy of oxygen or fluorine is less than that of succeeding element. When electron is added to n is equal to 2, the repulsion is more than when it is added to n equals 3 in case of chlorine or sulfur. Hence, option A is the correct answer. Please mark it. With this, we come to the conclusion of first part of periodic trends. In the next lecture, we will continue this chapter, that is periodic trends in chemical properties. Till then, goodbye.